Hello everyone. Today we are presenting a project our team built from scratch, a CPU scheduling simulator that focuses on something most simulators completely ignore: energy efficiency. This is basically a browser-based CPU scheduling simulator focused on uh, three algorithms: round robin, EDF, and EDF plus DVFS. Each algorithm computes total energy consumption, average turnaround time, and average wait time, and such things. This project is basically made to demonstrate how scheduling strategies and CPU frequencies scaling can affect both timing behavior and energy usage. Now, our groups and now my teammate will start his part.
Yeah, okay, just let me open the website first. So our simulator compares three scheduling algorithms side by side. The first is round robin. This is the classic one you study in OS class. Every task gets fixed time slice called quantum, and the CPU rotates between them. It's fair, but it's completely blind to the energy. It runs the CPU at full speed at all the time, whether the task is urgent or not. The second is EDF, earliest deadline first. This is smarter. Instead of rotating blindly, it always picks the task whose deadline is closest. This reduces deadline misses significantly. But again, it does not think about power at all. The third, and this is our main contribution, is energy aware EDF with DVFS. DVFS stands for dynamic voltage and frequency scaling. This idea is simple. If a task has a lot of time before its deadline, why run the CPU at full speed? We slow it down, and since power consumption scales with the square of voltage, even a small reduction in frequency gives massive energy savings. Our algorithm runs EDF for ordering, but before execution, each task checks how much slack the deadline minus remaining time the task has. Based on that, it assigns one of five frequency levels: ultra low, low, medium, high, or max. It tasks with lot of slack run slow. Tasks that are about to miss their deadline get full speed. Now my friend is going to continue.
Alright, let me show you this in action. So here is simulator running live in the browser. No installation needed, pure front end. You can see we have three inputs at the top. Task count, we'll keep this at 12. As you can see in the tooltip, this is the time slice for round robin. We'll keep it at 3. And the random seed ensures we get the same task every run, so a comparison is fair. Let me hit the run simulation. Okay, so look at what we got. 3 Gantt charts here, one for each algorithm. You can immediately see the difference in how tasks are distributed across time. Now I will scroll down to the performance metrics section. Total energy consumed here. So this is a key metric. You can see round robin is the highest EDF, is better, but energy aware EDF is slightly lower. That's DVF doing its job. Running tasks at reduced frequency whenever possible. Deadline misses. This tells us how many tasks failed to finish on time. Our EA EDF keeps us competitive with plain EDF, which proves we are saving energy without sacrificing reliability. And average turnaround time, this form when a task arrives to when it finishes. Again, EA EDF holds its own here. Now look at this, the CPU frequency distribution chart. See how much time is spent at ultra low and low? That's the energy saving happening in real time. And finally, the task table at the bottom. Every task, its arrival, burst, deadline, and you can directly compare the RR energy versus EA energy per task. You can literally see how by task how much energy we saved.
Now let me quickly talk about what each of us contributed. Vignesh designed and implemented the core EA EDF algorithm with DVFS frequency section logic. And Harvey built the entire front end, the Gantt charts, the metric display, and the task table. And I worked on the tooltip system you saw throughout the video. Every question mark you hovered over is a hover tooltip I added as a contributor, making the simulator accessible to anyone learning OS concepts for the first time. The biggest thing this project taught us is that scheduling isn't just a correctness problem, it's an optimization problem. The right schedule depends on what you are optimizing for. For mobile and embedded systems, energy is just as important as speed. If you want to try it yourself, the link is in the description, and thanks for watching.